We learned previously that the impulse response of a system is very important to determining how the system responds to an arbitrary input. In this presentation, we'll learn how to find the impulse response of a system. First, we'll note throughout the presentation we'll label the unit impulse response h of t. A unit impulse acting at time 0 can instantaneously change the value of the output signal y. Consider our water bucket system. A unit impulse in the input is equivalent to dumping in a gallon of water in a split second. After all, what we're saying is we're putting in a finite volume in an infinitesimal amount of time. This corresponds to putting the water in infinitely fast over an infinitesimal duration of time. In response, the height of the water in the bucket, y, will change discontinuously. That is, y at time 0 minus will not be equal to y at time 0 plus. Now it's important to point out that after time 0, there is no input to the system, x of t equals 0, and so the system is behaving after time 0 as if it was responding to just an initial condition. That is, it's behaving like the 0 input response. Now we know from before the 0 input response is the sum of the characteristic modes of the system. This is a key insight into understanding the unit impulse response. This is an important point, so let me emphasize it. The response for time t greater than 0 plus is due only to the state at time 0 plus, since there's no input acting for this time or any time later. That means the response to a unit impulse looks just like the 0 input response for times greater than 0 plus, and we know that the 0 input response is going to be the sum of characteristic modes. So we know that the unit impulse response looks like the sum of the characteristic mode terms for all time greater than 0 plus. Now we know if we have distinct roots, then the sum of the characteristic modes will be the coefficients ci times e to the lambda I t. And so this will be the form of the unit impulse response for time greater than 0 plus for the case of a system with distinct roots. So we see once again how important the characteristic modes are. They appeared in the response to initial conditions, the 0 input response, and now we see them playing a key role in the unit impulse response. So this insight tells us what the unit impulse response must look like for time t greater than 0 plus. But what about at time 0? Let's consider a trivial system. The output is equal to the input. The impulse response is clearly h of t equals delta of t. We put in an impulse and we'll get out an impulse. So it seems possible that the response at time t equals 0 may include an impulse at t equals 0, in addition to the characteristic modes. So we write the following: h of t equals a0 delta of t plus the sum of the characteristic modes. That will provide us the form of the impulse response for all time greater than or equal to 0. So two questions naturally arise. The first is, how do we find a0? And the second is, under what conditions will an impulse appear in the impulse response? So let's tackle these questions. Let's consider a system model consisting of q of d times y of t equals p of d times x of t. And q of d is a polynomial that's nth order in the differential operator. And p of d is also nth order in the differential operator. This system will have an impulse response that's given by the equation h of t equals a0 times delta of t plus the sum of the characteristic modes. And a0 will be equal to the coefficient b0. This is the coefficient of p of d that multiplies the nth derivative operator. So if the coefficient b0 is equal to 0, the impulse response will have the form h of t equals the sum of the characteristic modes. That is, there will be no impulse at time 0 in the response h of t. We had previously written our polynomials q of d and p of d as shown here, and you'll note that b0 is equal to 0 if the order of the p of d polynomial, called m, is less than the order of the q of d polynomial, called n. This is the condition which determines whether the impulse response will have an impulse in it or not. That is, it determines whether an impulse will pass through a system when it is presented as an input to the system. Here is the method by which we can find the impulse response of a system. The system we're going to consider is q of d times y of t equals p of d times x of t, and we'll assume that q of d and p of d are both nth order polynomials in the differential operator d. The response will have the form h of t equals b0 delta of t plus the quantity p of d times yn of t multiplied by the unit step u of t. Yn here is a linear combination of the characteristic modes. The coefficients in this linear combination are chosen such that the following conditions are satisfied. Yn at time 0 is 0, and the same is true for all the derivatives up to the n-2 derivative of yn. Then the n-1 derivative of yn at time 0 is set equal to 1. Once we have determined yn, we then need to multiply it by p of d. Of course, multiplying by p of d is multiplying by a polynomial in the differential operator, which means we'll be taking various derivatives of yn and adding them together along with the coefficients of p of d. Once we've determined this, we multiply it by the unit step u of t, since this part must be causal. The coefficient b0, of course, which multiplies the Dirac delta in h of t, is found as the coefficient of the nth derivative in p of d. So this procedure allows you to find the impulse response h of t from the differential equation of the system. Now let's look at an example. Suppose you wish to find h of t for the following differential equation. q of d is d squared plus 5d plus 6, and p of d is d plus 1. We note that the order of q of d, n, is 2, and the order of p of d, m, is 1. So m is less than n, and the coefficient b0 is 0. That tells us that the impulse response will not have a Dirac delta in it, and will only consist of the term quantity p of d times yn of t multiplied by u of t. So now we need to find yn. We know it will be a combination of the characteristic modes, c1 e to the lambda 1t plus c2 e to the lambda 2t. Lambda 1 and lambda 2 are the roots of the characteristic polynomial, which is q of lambda equals lambda squared plus 5 lambda plus 6 equals 0. You notice the form of the polynomial here is the same as q of d in the differential equation. Solving, we find lambda 1 equals minus 2 and lambda 2 equals minus 3. So we know yn of t will be equal to c1 e to the minus 2t plus c2 e to the minus 3t. And our goal now is to find c1 and c2. We find these values by using the initial conditions given in the procedure. Specifically, yn at time 0 must be equal to 0, and yn dot at time 0 must be equal to 1. We now simply take the derivative of yn, and we find it to be minus 2c1 e to the minus 2t plus minus 3c2 e to the minus 3t. We set the time equal to 0, and we have yn dot at time 0, which must be equal to 1. So 1 must be equal to minus 2c1 minus 3c2. And from the condition yn at time 0 equals 0, we know that c1 must equal minus c2. Solving these two equations in the black boxes, we can find c1 and c2. c1 is equal to 1 and c2 is equal to minus 1. So this tells us that yn of t will be equal to e to the minus 2t minus e to the minus 3t. Now yn is not h of t. We need to take yn and multiply it by the polynomial differential operator p of d. That was the polynomial differential operator that was multiplying x of t in our differential equation. So, in this case, p of d is d plus 1, and we apply that to yn of t, which is e to the minus 2t minus e to the minus 3t. Then the next step in computing h of t is to distribute the d plus 1 onto the e to the minus 2t minus e to the minus 3t. Carrying out this distribution, we find the expression on the last line on this page. Now recall that the differential operator, capital D, is equal to d dt. So we'll apply d dt to all the terms that capital D is multiplying, which yields the expressions shown here. Now collect together the like terms and simplify. And this yields the impulse response h of t. It's equal to the quantity e to the minus 2t plus 2 e to the minus 3t multiplied by u of t. You can see that finding the impulse response h of t is a rather involved procedure. First you have to find yn, and then you have to carry out the operation of p of d on yn. You should note that this method only works on linear systems which are described by the differential equation q of d times y of t equals p of d times x of t. If the linear system is not in this form, we cannot use this method to find h of t.